Hello everyone, welcome back to Math-211. Great work on exam 1 or midterm 1. There's 4 more to go. So in this video, we'll talk about proper mathematical syntax and I'll showcase 2 examples for you. One of them will involve trig and the other one will involve integration by parts. We'll discuss the reverse chain rule with a bunch of examples and a generalization. And then we'll talk about the newest addition to your Dropbox known as the class performance file. So we have been marching along in Calculus 2, and you may have noticed that a lot of the feedback on your P-sets include comments like, don't forget your equal signs, or perhaps you're missing a dx. Well, now it's time to begin refining your ability in writing in the language of mathematics. You want to start breaking down those bad habits and then fostering new ones. And the motivation behind this is that what you really want to achieve is having the ability to articulate your ideas. I mean, these thoughts and processes on paper in such a way that it is easy to understand, and anyone who sees it can understand it too. And syntax will play a big role in doing that. So if you recall from the optional problem set for midterm 1, below I've highlighted most of the common notational mistakes that students make, namely the equal signs and the dx's. And I know it's typed out, but nonetheless, I want you to detect that moving from one step to the next step, it's very clear what I'm trying to achieve. I can follow the logic within this problem very, very easily. So for example, in line 1, I applied a power reduction formula for the cosine squared of x. And of course, I'm doing this because I'm not a big fan of the cosine squared and the cosine not sharing the same arguments. Or even from line 3 to line 4, where I applied the linearity of integration, where I rewrote this integral of a sum as a sum of integrals. And by the way, you don't always have to rewrite the integral of a sum as a sum of integrals. However, I do recommend that if one of the terms within the integrand of your integral requires more attention, such as an integration by parts or perhaps a substitution, then that's when I do recommend that you do apply the linearity of integration and rewrite that sum as a sum of integrals. All right. And of course, in my final line, in line 6, I boxed my final answer. And since problem set 1, y'all have been doing a tremendously good job at not forgetting that constant of integration. Because again, that constant of integration is telling us, or when we're computing the indefinite integral, we're really looking for the most general antiderivative of f. So antiderivative. And again, I'm not connecting equivalent expressions with arrows. I'm using equal signs all the way through. So a bit of an aside on the dx. We sometimes refer to the dx as the differential x. And it tells us to which variable are we integrating with respect to the function, in this case it's f. So here we're saying that we're integrating f with respect to x. And I know that it might not be of much concern now, but if you go on to multivariate calculus, those differentials at the end of your integral suddenly become very important. And if we're looking at the definite case for an integral, these dx's also tell us what kind of bounds or what kind of numbers are being tacked onto that integral sign. So what I'm saying here is that a and b are values of x. That's why when you perform a substitution for a definite integral, if you want to evaluate that definite integral, let's say if you choose u in terms of u, you also have to re-express your bounds to be in terms of u because the original bounds of x were values of x. They weren't values of u. And if you remember back all the way from Calculus 1, we remember that the definite integral is just a continuous analog of the Riemann sum with this delta x approaching 0. So we apply the limit as delta x approaches 0. And of course, as a consequence of that, we also know that the number of partitions n approaches infinity. Okay, so in the next problem, we're doing integration by parts. So I can define u to be x, and then by default, I have no choice. My differential v must be the secant squared of x dx. And the biggest thing that I see here for integration by parts from students is that they forget the dx after defining dv, and then they also forget to write the dx after computing my differential u. And as I mentioned in the last slide, we don't use arrows to connect equivalencies. However, this particular arrow is saying, well, hey, after I found all the components for integration by parts, I'm continuing my equality here. And I want to emphasize that this arrow is not a substitute for an equal sign. So, of course, after applying integration by parts, we need to remember that since this is a definite integral, we're evaluating the uv part of integration by parts from the lower bound of 0 to an upper bound of pi over 4. And another thing to note towards the end of this problem is that I actually dropped the absolute value bars off the natural log. And the reason for this is because we know that the cosine of pi over 4 is always positive. And so those absolute values are just redundant if you were to write them in the final answer. Some other things to highlight in this particular section is the fact that our antiderivative, capital F of x, is clearly defined. And so it's x times the tangent of x plus the natural log of the absolute value of cosine of x. And again, we're evaluating this antiderivative from a lower bound of 0 all the way to an upper bound of pi over 4. All right. Okay, let's talk about the reverse chain rule. So the reverse chain rule is just integration by substitution. And I've done 4 examples for you, and by now all of these integrals should be really, really easy. And so let's take a look at the first one. For the first one, I can define u to be 3 times theta minus pi. This means that my differential u happens to be 3 times d theta. And so how I got this 1/3 was by dividing by 3 on both sides of that differential u. So we'll have 1/3 differential u. So this is the same thing as 1/3 times the differential of u is equal to d theta. So again, that's how this constant came about. Similarly, for the next integral, I can define u to be 7x plus 4. And then my differential u happens to be 7 times dx. Moving along, the integral of secant squared of v over 2, again, I can define u to be v over 2. Then my differential u happens to be 1/2 times dv. So again, that's how we got this 2 from this 1/2 after multiplying both sides by 2. And then for the last one, I can define u to be 5 minus 9y. So then my differential u would be defined to be -9 times dy. And so the antiderivative or the indefinite integral of dy over the square root of 5 minus 9y would be 2 times the square root of 5 minus 9y divided by -9. So that's how we got the 2/9 here, right? Now, if you look at these 4 examples as a whole, I want you to notice that these were all composition functions. So in the first example, we had a linear function composition within a trig function. For the next example, we had a linear function compositioned into a rational function, and so forth and so forth. So it turns out that we can actually generalize this idea of reverse chain rule, or again, synonymously, integration by substitution. That's really what it is. So let's suppose that I'm taking the indefinite integral of some function, let's call the function f, and we're going to apply a linear composition, or we're going to composition a linear function into f. So let's suppose that we call it alpha times x plus beta. Here we're assuming that alpha and beta are constants. We are integrating this with respect to x. Well, if you notice that for the 4 examples above, the antiderivative, or all the boxed answers next to the indefinite integrals, always had the antiderivative, meaning capital F of x, multiplied by this constant, which was the reciprocal of the coefficient of the linear function. In this case, for the first one, it'll be the linear function 3 theta minus pi. So the reciprocal of the coefficient of the theta happens to be 1/3. The next one happens to be 1/7. The next one happens to be 2, and so forth and so forth. And so this generalizes very nicely. So we'll have, again, the reciprocal of the x, or the coefficient of x. So we'll have 1 over alpha times the antiderivative of f with alpha x plus beta. All right. And again, we're tacking on a constant of integration because we're generating a family of functions, or the most general antiderivative. And this will be true for all constants alpha and beta where alpha is not equal to 0. Because in the case that alpha does equal 0, we just have f of beta, and f of beta will also be a constant, right? And so I've typesetted this out for all of you. Okay, so let's move on to the newest addition that is housed inside your Dropbox. And again, it's called the class performance file. So it'll be at the very top when you log in inside your folder. And in addition to seeing stats for the entire class, you'll also be able to see breakdowns for each problem, along with the score distribution. So let's go ahead and take a look at what it looks like. As of now, it only has 3 pages. That's because you've only turned in 3 p-sets. Let's go ahead and scroll all the way down to problem set 3. And you can see that it's actually broken down into three main sections, namely the submissions, the summary, the breakdown, and then the distribution. The submissions is pretty self-explanatory. One thing that I do want to emphasize is that all the numbers from the summary and below, they were all computed with student submissions only. So in other words, all the non-submissions were excluded in the computation of this data. So we didn't have this 10 non-submissions, those zeros pulling down all of these averages and affecting the rest of the data. And one thing that I do want to highlight in terms of the breakdown is, I guess in terms of utility, let's suppose that you're looking at the last problem. If you've noticed that on your feedback document, you didn't do so well compared to the rest of the problems. Well, you can actually see here that that was pretty consistent with the rest of the class. So it's something to note. And the fact that this particular problem was something that students had trouble with might be an indicator that it might pop up on a future exam or so. So the distribution. Here, the way you can look at this is that below we have a bunch of bins. And so suppose that we're looking at the interval from 90 to 100. This is what we call the bin from 90 to 100. We can see that 17 students scored between a 90 to 100. And most of the students are actually scoring hundreds because of the provision that was established in the beginning of the course or in the construction of how we look at these p-sets. Another example is that someone scored between a 50 and 60 on p-set 3 and so forth and so forth. And so you can see that this distribution, excluding the bin from 0 to 10, is skewed towards the left. And we can see that the average is an 84.4, so that means I can put a balancing point or some kind of fulcrum right here. So the average is actually pretty high for this particular p-set, and that's really good. It is the expectation that the submission count does go up, so you should be submitting your p-sets because they are a big chunk of your final grade, and you can't get an A without doing well on the p-sets. And again, how you should be viewing these p-sets is that they're very low stakes. And the recommendation that I have here is that you do every single problem and you try. Should you have any questions, come visit us in office hours and we'll be more than happy to help. All right, so that is all that I have for you today, and I will see you next time.